Okay, let's start. Thank you for coming, and I'm especially glad to make this talk to two authors of the Hitchhiker models, Jennifer Chase and Kristen Works. So this is about social networks. So I want to briefly outline what is the social networks and what properties we want to model. A network consists of nodes and edges, and in the case of social networks, nodes are just people, or you may say agents, economic agents, and there are different types of connections. So edges are some connections between people, like personal connections or business connections or anything else. So one possibility is that this is an online social network, so nodes are just accounts of different people, and edges are connections in the online network. And so there are two types of connections, directed or undirected. Directed like following, and undirected like friendship. And one advantage of online networks is that they may be analyzed completely. So you may just scroll the whole Facebook and just analyze the resulting network. Okay, and so many different networks were analyzed, and there are several common properties that may not occur in other types of networks. Okay, so the first property is small diameter, so-called 6 degrees of separation. So first there is the stylized fact that from between any two people on the Earth, there is a chain no longer than 6, and this chain consists of only personal acquaintances, so-called first-name acquaintances. So, of course, literally this is not true, but there are many evidence that this is true to some extent. For instance, if you count the diameter of Facebook or of Twitter, so you may find that that diameter is something around 10, and average distance between two vertices is even smaller than 6, it's like 4.5. Okay, so this is the first property. Another property is clustering, and I have an illustration. So this is my neighbors in Facebook. And so here are two properties. So first, there are a lot of clusters that are densely connected within each other and are not connected to each other. Okay, so and another property is that there are just many edges in this network. So my friends often are friends to each other also. Okay, so this can be measured by clustering coefficient. So loosely speaking, clustering coefficient measures the number of triangles. So there is a local clustering coefficient measures the number of triangles among neighbors of one vertex, and global clustering coefficient measures the number of triangles in the whole graph. Okay, so somehow this is the ratio between actual number of triangles to potential number of triangles. Okay, so let me skip the formula. And also, in real networks like Facebook or something like this, clustering coefficient is very high. It's like 10% or something like this. Okay, so another property is scale freeness. So his stylized fact is that in every social networks there are hubs. So to say vertices with very high degree. So people who have a lot of friends. So much more than average and many times more than average. And this may be measured by the degree distribution, and the tail of this distribution is not exponentially low, but is distributed according to power law. And this may be seen in the graph at log scale. So and I have one illustration from one research. So here are graphs of, so here are the distribution functions of out degree and in degrees in 4 different networks. So and many they look like a straight line, with some exceptions that occur due to some local rules of respective networks. Greater than. So this is distribution function. Okay, so it's a brief summary. So there are 3 main properties: small average distance, high clustering, and scale freeness. And also there are some minor properties like assortativity and high degree vertices are connected to each other, and some other features. So, and the main question is how and why do all these features emerge? Okay, so now let us talk about the existing models. So there are 2 main approaches. So one approach is the random graph approach, that you specify some randomness distribution on all possible networks, and then you just count the expectation of all these characteristics. So you count expected clustering coefficient, expected average distance, and so on. And there is a plenty of such models. And we may say that different models are good for different properties. So say Watt-Strogatz model is good for small diameter and for high clustering, but is not good for power law degree distribution. And Balabashvili-Ardan is good for power law degree distribution, but not always good for clustering coefficient, and so on. And also, they all have inherent disadvantage that they do not answer the question why these features emerge. So they may answer the question how you can obtain such features from some artificial process, but they cannot answer how they emerge in reality. Okay, so another approach is game-theoretic approach. This is much more natural in case you ask why all these features emerge. Because agents in the network, they are not just mathematical abstractions, they are people, and they make some decisions with whom to make a connection, or with whom to not make connection, so on. And they have some utility from this connection, probably. There are several models where agents form connection directly. So there is just some cost of making a connection to another agent, and all agents simultaneously make this decision. They purchase the costs, they purchase the connections, and they get some utility from something, maybe from a connection itself, maybe from a chain of connections, and so on. But usually, in these models, a very regular structure emerge. So this structure like a complete graph, or a cycle, or a star, or something like this. So they do not have all nice properties to a very large extent. Okay, so and now we turn to the Hitch-Hiker approach. So it is also game theoretic, but here a connection may be purchased indirectly. So in some sense, one agent may purchase a connection between a second and a third agents. Okay, so here many nice properties may be obtained in equilibrium, and this is an advantage. And probably a disadvantage is that there are too many equilibria. So good configurations may occur in equilibrium, but many not so good configurations also may occur in equilibrium. And so our goal is to somehow to extend this model, so for refining the set of equilibria. So to throw out bad equilibria and to keep good equilibria. Okay, so now let me specify. So there is one notion called affiliation networks, and this is connected to hitchhiker model. So affiliation network is the following. Initially, there is a bipartite graph between agents and activities, like this. And after that, we construct a graph between agents, so where an edge exists if two agents participate in one activity. So in this case, the graph is the following. And probably this is a good model for social networks because, in fact, there are some clubs, some companies, some collectives where everyone knows everyone, and every person participates in several such groups. And that's why in a real social graph there are many cliques, many complete subgraphs. And this, the idea of affiliation networks lies in the bottom of the hitchhiker model. So maybe the main idea of the hitchhiker model is that these groups are formed not from outside, but they are formed by people themselves. Okay, so now let me specify the model. So there is some set of agents, a finite set of agents, and each agent may organize a gathering. So a gathering is just a subset of the whole set of agents, and also each gathering has characteristic called rate. So this is just a positive number. And all these gatherings are costly. So there are fixed costs and marginal costs for every extra agent, and both fixed cost and marginal cost are multiplied by rate. Well, and each agent may organize many different gatherings with different rates, and so the total cost of one gathering is its rate times fixed cost plus marginal cost multiplied by the number of invited person. And the total cost of one agent is the sum of costs of all gathering organized by her. Okay, so this is the cost side, and now the benefit side. So a connection between two agents is formed if they jointly participate in gatherings with a total rate greater than 1. And it doesn't matter who had organized these gatherings. So they may be organized by the first agent, they may be organized by the second agent, and they may be organized by some third party who just invited them both to her gathering. And each link delivers some constant utility to both agents. Okay, so these are formulas saying the same. So, and we obtain a very complex game, but this is a one-shot game. So first, what's the game? So strategy of an agent is a set of gatherings together with rates. So, and they independently choose these sets, and after that, a network is formed, and they receive their profits. And we may apply the solution concept just Nash equilibrium. And the main question is what configurations may arise in some equilibrium and which may not arise in an equilibrium. Okay, so here, this is an example from the original paper. So, and we may see that the configuration, so this is one example, and a configuration without triangles is not supportable at all. And if there are many triangles, then they are supportable for some values of parameters. So this is just an example, and also there are some nice theorems from the original paper. So first, star configuration that has zero clustering coefficient is not supportable. Moreover, any supportable graph has sufficiently high clustering coefficient, and also parallel law is also supportable in some equilibrium. But there are too many equilibria, so clustering coefficient may be not as high as it is in real networks, and also some other degree distribution may also arise. And maybe the most disadvantageous thing is that if at least one non-empty configuration is supportable, then the complete graph is also supportable. And the reason for it is increasing returns to scale, because the larger the gathering, the cheaper is the one connection in it. Because if you form a gathering of k agents, then the cost is proportional to k, and the number of connections is proportional to k squared. Okay, so this is the main idea. Well, and we try to attack this this upsetting fact, try to somehow change the model so that this fact is no longer true. So our first idea was inspired by economic geography models, and the idea was to introduce distance, to say that all agents live in some metric space. This metric space may represent just geographic space, that all agents live in different points in, say, sphere, and if they live close to each other, then it's not so costly to invite each other to the gathering, and if they live far away, then it's much more costly. And also, this space may represent some tasters or attitudes. So, because if agents have close interests, then it's also simpler to make a connection. Okay, so we just multiply the cost of inviting an agent by the distance between their points. Well, so we began from analyzing the simplest case when the space is one-dimensional, and also there are no borders. That means that this is a circle, and the distribution is just uniform. And the first idea is that every agent should invite just its vicinity and some structure, wheel-like structure should emerge. But this intuition is wrong, because if two agents live close to each other, then they would be invited by many. They would be invited together to other gatherings, and that's why they do not have an incentive to invite each other, because they already have an edge between them. So this would not be an equilibrium, and in fact, the only symmetric equilibrium when every agent uses the same strategy is not very natural. Is that just a person? So this, instead of this segment, she invites something like this. Well, so that seems that maybe if in the simplest case we obtain such strange results, so maybe we should not use literally this model. Maybe we should use another equilibrium concept or something like this. Okay, so this was our first idea. So, and this idea may be generalized. And this for an intuition, there is just distance in not a real distance, but some coefficient, some multiplicator, of course. It may not be metric. It even may not be symmetric. But this is marginal cost is multiplied by the sum of this coefficient. Okay, so two previous models are just subcases, and here we analyzed another situation when this cost depends only on the person who invites. So the intuition is that some people make a lot of parties, a lot of gatherings, and others do not organize anything. And maybe those for whom it's simple do it, and those for whom it's difficult do not do it. So and here we didn't reach our goal, but we had some interesting results. So basically, this case is pretty like the original model, but it is very useful for comparative statics. For instance, one property is that there is some threshold in C, such that with greater C there will be only empty graph equilibrium, and with lower C there will be more equilibria. And the first equilibrium the first non-empty equilibria that occurs is the complete graph equilibria. But in this graph, in this complete graph, all agents bear the same costs. So that means that if an agent has a high cost of invitation, then he invites few people with few rates. And if an agent has low cost of invitation, then he invites with high rates. Okay.
So the complete graph is being formed together by
Yes.
each bearing his personalized part of the cost.
Yes, and this personalized part is reversely proportional.
His ability to
Yes, exactly. Okay, so we also have some more ideas. So another idea is to make heterogeneous profits that not cost depends on two agents, but profits from a connection from an agent that depends on identities of these agents. But we obtain then in some cases this expression is equivalent to the previous one. That is, increasing this pi is equivalent to reducing rho in the previous extension. Well, and another idea that we started to analyze 2 weeks ago is the idea of concave profits of diminished marginal utility. Specifically, every next connection brings less utility to the agent, and we use just geometric progression. Then, okay, direct connection, yes. So if you have 1,000 connections, then every extra connection brings you less utility than if you have 10 connections. Okay, and so we obtained, in this model, we obtained the bound on maximum click size. And this is good news, because here the complete graph may not emerge. And so this is our first result in this extension. We are continuing to investigate it. Okay, so also we have some more ideas that we have not analyzed yet. For instance, it may be then in large gathering, like a, say, 1,000 people conference, it's harder to make a connection with the participant of it. And if, say, there are 10 people party, then it's very simple to make a connection. Okay, so also we have some plans. let me conclude. So there are two main approaches to social network formation. One is random graph approach, and the other is game-theoretic approach. And random graph approach is more successful in terms of describing the real network's features. But game-theoretic approach is more natural. And if we have a model, a game-theoretic model that describes all features that we see in real networks, then probably this will be a real probably this model will describe the real process of network formation. But current models are not so explanatory, and so we are trying to make them more explanatory. Okay, and also it is hard to make a model that would be also that would be simultaneously tractable and will have all features from the reality. Okay, thank you for your attention.
Maybe it is better to see in not two approaches, but four approaches. Here is technical models, here is game theoretical models, and here we have structured models like geometric graph, when there is a structure on the space of, when agents live, say, in a metric space or whatever, and this is without structure. And probably this is the what we are searching for, the structured game theoretic approach. So when the vertices of the network are people who make decisions, but they simultaneously they live in some metric space, and here is geometric, technical geometric models. It's like simple geometric graph when those who are close to each other they form a connection. And this
with some
very
probability.
high coefficient, clustering coefficient, but other properties are bad. And the game theoretic models without structure, there are lots of such models, and technical models, there are lots of such models. So here, here, and here, there are lots of models, and we look to this last part in this scheme.
Thank you.
So are there more questions or comments? Back there?
It's possible to use this model for forecasting social events in local and global areas.
For recast,
Social events.
You should repeat the question. So is it possible to use this model to forecasting social events?
so you mean that somebody wants to make a lot of connections and he organizes a gathering?
Maybe
Well-
during the Facebook analysis, you have not only access to the graph itself, but also there are actual events. So you can somehow try to compare the theory with practice only more on the lower level.
Well, in fact, Facebook events are not organized, not always organized for making a connection, but they may be organized for some actual activity.
Also,
In fact, there are some parties. They are indeed connected for making. They are indeed organized for making connections, like devirtualizing, Also, there are some PGP parties for exchanging some keys. And probably you should analyze these gatherings, but not the whole bunch of them.
Also, lots of things that happen in the real world are bilateral and not just paid for by one side. So at best, this might be able to model those events which get paid for by one side, but the other side has no choice but to show up. So in terms of a revolution, I'm not sure about that. Okay, on the other hand, a market crash, maybe the other side has no choice but to show up.
Daniel, what is the current best result in going to correct degree distribution by models with such approach? What is the gap between the degree distributions that you received and
no, the gap is that the right degree distribution may occur in equilibrium, but also many other distributions may also occur.
okay?
So, have I answered?
Yes.
So when you got to this modified model where my benefit of having the k's friend is only q to the k, does that lead to capping off the degree distribution, or do you still have power law degree distributions?
You mean this model?
Yes, this one.
It's ongoing, so we haven't answered yet.
Any other questions?
Very short question. So what framework have been used for graph analysis? And how big graphs which have been analyzed?
No, this was just a theoretical model. So we ourselves didn't analyze the graphs, but we used those analyzed by others.
Okay, why don't we thank Daniil and then reconvene in about 25 minutes.